Moving average or running mean. Is there a scipy function or numpy function or module for Python that calculates the running mean of a 1D array given a specific window?
For a short, fast solution that does the whole thing in one loop, without dependencies, the code below works great.
Update. More efficient solutions have been proposed, uniform_filter1D from scipy being probably the best among the standard third-party libraries, and some newer or specialized libraries are available too. You can use np.convol for that. Explanation. The running mean is a case of the mathematical operation of convolution. For the running mean, you slide a window along the input and compute the mean of the window's contents. For discrete 1D signals, convolution is the same thing, except instead of the mean you compute an arbitrary linear combination, i.e., multiply each element by a corresponding coefficient and add up the results. Those coefficients, one for each position in the window, are sometimes called the convolution kernel. The arithmetic mean of n values is x_1 plus x_2 plus ... plus x_n, n, so the corresponding kernel is 1/n, 1/n, ... 1/n, and that's exactly what we get by using np.1's n/n. Edges. The mode argument of np.convol specifies how to handle the edges. I chose the valid mode here because I think that's how most people expect the running mean to work, but you may have other priorities. Here is a plot that illustrates the difference between the modes.
Efficient solution. Convolution is much better than straightforward approach, but, I guess, it uses FFT and thus quite slow. However, especially for computing the running mean, the following approach works fine. The code to check. Note that numpy.allClose_result1, result2 is true. Two methods are equivalent. The greater n, the greater difference in time. Warning, although CumSum is faster, there will be increased floating point error that may cause your results to be invalid/incorrect/unacceptable. The comments pointed out this floating point error issue here, but I am making it more obvious here in the answer. The more points you accumulate over, the greater the floating point error, so 1e5 points is noticeable, 1e6 points is more significant, more than 1e6, and you may want to resetting the accumulators. You can cheat by using np.long_double, but your floating point error still will get significant for relatively large number of points, around in GT, 1e5, but depends on your data. You can plot the error and see it increasing relatively fast. The convolve solution is slower but does not have this floating point loss of precision. The uniform_filter1D solution is faster than this CumSum solution and does not have this floating point loss of precision.
Update.
The example below shows the old pandas.rolling_mean function which has been removed in recent versions of pandas. A modern equivalent of that function call would use pandas.series.rolling. Pandas is more suitable for this than numpy or scipy. Its function rolling_mean does the job conveniently. It also returns a numpy array when the input is an array. It is difficult to beat rolling_mean in performance with any custom pure Python implementation. Here is an example performance against two of the proposed solutions. There are also nice options as to how to deal with the edge values.
If you want to see more, please consider subscribing.